Today, we will be presenting how we can enhance gravitational wave detection using quantum optics technique known as squeeze light, which is currently implemented in detectors like LIGO. Nearly a century after Albert Einstein predicted gravitational wave as a consequence of general relativity, their direct detection has become one of the most important achievements in modern physics. These waves are ripple in space-time produced by accelerating massive bodies such as merging black hole and neutron stars. Detecting gravitational waves is extremely challenging because they induce strain amplitude of order 10 to the power minus 12, which corresponds to displacement changes of 10 to the power minus 18 meters. To measure such a tiny signals, detector like LIGO uses kilometer scale laser interferometer. However, their sensitivity is fundamentally limited by quantum noise arising from quantum nature of light itself. LIGO operates using Michelson-Morley interferometer, where laser beam is split into two perpendicular arms reflected by mirrors and recombined to produce an interference pattern. A passing gravitational wave causes a differential change in arm length. Delta L is equal to delta x minus delta y. This results in a phase shift in combined beam, which is detected as signal. However, achieving the required sensitivity is limited by both classical noise, seismic and thermal, and quantum noise, which with the later becoming dominant at higher precision. At such high precision, classical noise sources like thermal or seismic noise can be reduced significantly. However, we encounter a fundamental limitation known as quantum noise, which arises from the quantum nature of light itself. There are two main contributions: short noise, radiation pressure noise. Short noise. Short noise arises because light consists of discrete photons. The arrival of photon at the detector is random, leading to statistical fluctuation. These fluctuations scale as square root of number of photons, which introduces uncertainty in measured signal. These noise mainly affect the phase measurement and dominate at high frequency. Radiation pressure noise. Radiation pressure noise. At low frequency, radiation pressure noise become important. Photons carry momentum, and when they strike the mirror, they exert a force. Fluctuation in photon number lead to fluctuation in this force, causing the mirror to move randomly. So in this region, mirror themselves become noise. Standard quantum. There, these two type of noises create a trade-off. If we increase laser power, short noise decreases, but radiation pressure noise increases. These lead to fundamental limit called the standard quantum limit, beyond which classical strategies cannot improve sensitivity. Vacuum fluctuation. Even in absence of light, quantum theory predicts the vacuum is not empty, but filled with fluctuation of electromagnetic. This vacuum fluctuation enter the interferometer through the antisymmetric port, mixes with the signal, and appear as noise in output. Thus, quantum noise fundamentally originates from these vacuum fluctuations. We describe light using two quadrants: the in-phase component, the out-of-phase component. These are conjugate variable and obey the Heisenberg uncertainty principle. These means we cannot simultaneously reduce uncertainty in both components. In a standard laser or coherent state, the uncertainty is equally distributed between quadrants. This gives a symmetric uncertainty distribution and set the baseline quantum noise level for measurement. In a squeezed state, we redistribute these uncertainties. We reduce noise in one quadrature while increasing it in the other. Importantly, the total uncertain, uncertainty still satisfies the Heisenberg principle. This allows us to reduce noise in the specific quadrature relevant for measurement. In LIGO, instead of allowing normal vacuum fluctuation to enter, we inject a squeezed vacuum state. By carefully choosing the squeezed angle, we reduce uncertainty in phase quadrature, which directly affect the measurement. This leads to a reduction in short noise and improved sensitivity beyond the standard quantum limit. The impact of quantum noise depends on frequency. At high frequency, short noise dominate, so squeezing is very effective. At low frequency, radiation pressure noise dominate, making improvement more challenging. A key achievement of this work is extending sensitivity improvement down to about 150 Hz, which is crucial for astrophysical sources. So achieving squeezing at low frequency is difficult due to seismic noise, non-linear coupling of noises, scattering light constraint, precision phase control of squeeze, require extremely high experimental precision. So next, my friend Sachin Raj will be telling you about the structure of LIGO.
So now I will explain the experimental setup of the Michelson interferometer. So basically the experiment was carried out towards the end of 2011 on the LIGO detector at Hanford, Washington, known as H1. The name H1 corresponds to the Hanford, Washington, and also we are using here H1 laser. And the basic optical layout of the detector is shown in the left side of this diagram. So basically the interferometer light source, which is H1 laser, which is just neodymium, yttrium, aluminum, germanium laser, whose wavelength is 1064 nanometer. And this is a solid state laser, and this laser is stabilized in frequency and intensity. And now this laser the output source of this laser is the vacuum, a squeezed vacuum, and the squeezed vacuum is then split by the beam splitter into two arms of Michelson, and there is also a Fabry parrot cavity which increases the phase sensitivity by bouncing the light 130 times in each arm. And the Michelson interferometer is operated on a dark frame, which means the beam splitter, which is shown here on the left side of the diagram, it uses the difference of the intensity. So initially the experiment is set up in such a way that the initial electric field which is coming from this top path and which is coming from this left path, they cancels. So without gravitational field, this beam splitter detects zero signal. And and now a partially transmitting mirror between the laser and beam splitter. This forms the power recycling cavity, which increases the power incident on the beam splitter by a factor of 40. And to isolate the experimental setup from terrestrial forces such as seismic noise, the power recycling mirror, the beam splitter, and the arm cavity mirrors are all suspended as pendulum on vibrational isolated platforms. Now we will understand how we can detect gravitational field using this kind of interferometer. So basically, a passing gravitational wave produces a differential change in the length of the arm cavities. Generally, one arm gets shorter while the orthogonal arms gets longer, and this causes the signal field to appear at the antisymmetric fold, which is proportional to the wave amplitude. More formally, we can describe the gravitational wave traveling through other by jet space by metric g mu nu is equal to eta mu nu plus h mu nu. Here eta mu nu is our original mean positive metric and h mu nu is the perturbing metric. And for the special case of gravitational wave which is traveling along the z-axis, the metric perturbation can be written in this form, where time components are zero, and here we have a block diagonal form. And now let the arms of the Michelson interferometer be aligned along the x-axis and y-axis, and beam splitter is at the origin. So now we first consider light which is traveling along the x-axis. So it's governed by this equation d square is the line element, and for light this is zero, and this is just equal to g mu nu dx nu, and now expanding this term for zeroth component and its component, because since they are only considering the light traveling along the x-axis. So finally this gives minus c square dt square plus 1 plus h11, which is just gravitational wave, and this is a function of 2 pi f t. F is the frequency, t minus k dot x, k is the wave number of the gravitational wave, times dx square. And to find the time elapsed of going light from one point to another point along the x-axis, we integrate infinitesimal time dt from 0 to tau, and this is just 1 by c integral 0 to L. Here is L is the length of the x-axis, under root 1 plus h11 dx. And if we approximate if we assume the approximation that gravitational wave is very small, then we can use the binomial expansion, and we can write under root 1 plus h11 h1 plus h11 by 2. And so this is a straightforward integral. And so total time elapsed for the light to go from beam splitter to the vacuum envelope, and coming from vacuum envelope to beam splitter, this is just twice. This is the twice times of this time. And if we consider the similar time interval for light to go in the vertical y-axis, then total time difference which is measured at the beam splitter is h times 12 by c. Here h is the amplitude of the gravitational wave. Here we are assuming that the frequency of the gravitational wave is very small, and the amplitude is also very small. And this is the phase of t times some constant of which is 12 by c, which is the parameter of R interferometer. And this time difference causes a phase difference at the beam splitter, and this phase difference is directly related to the LO oscillator, linear oscillator, and this phase difference is h times tau times 2 pi c by lambda. Now for unfiltered order length L, a gravitational wave which we, and here we saw that the phase difference is directly related to the amplitude of the gravitational wave. And for typical astrophysical sources, which are basically 10 to 100 megaparsec away, such as in a spiral or merging of two binary neutron stars or black hole or some kind of supernova, or our terrestrial detectors must measure a strength at the level of 10 to the power minus 21 or smaller with some offset.
Okay, so now I will discuss about this particular section of the setup. This is where the squeezed vacuum is engineered or produced, and then that eventually enters a LIGO system. So in order to produce a squeezed vacuum, we need to have a crystal, a system. So that crystal is basically this PP-KTP crystal, which is a very nonlinear crystal. And this is what they have used in the paper. And what we see here is the SPDC, that is the spontaneous parametric down conversion. So what does it mean is, if we have a high power pump laser or pump light coming and hitting the crystal, that is, let's say, the green light of 532 nanometer, it eventually splits equally into two lower energy photons of frequency less, like 1064 nanometer each. That is the half of the pump laser that we injected into the system. So in order to go through it in detail, what happens is, first we have a second order nonlinear crystal. So in these crystals, usually we have a polarization, second order term of the polarization, which depends on the square of the electric field, coupled with the Xi2. This Xi2 is usually non-zero for such crystals. Now, due to this kind of polarization. The interaction Hamiltonian between the crystal and the incoming light, pump light, basically looks something like this. So as you can see, it also incorporates the nature of the pump, that is the phase of the pump and the strength of the pump. And also we see this kind of two terms, basically the operators that creates or destroys two photons together in pairs. This is very similar. It rings a bell that it looks very similar to the squeezing operator. So how the system evolves is basically using this transformation, and this is very similar to the squeezing operators we have discussed in class, where there is this a square and a dagger square terms involving. And then there is this coefficient of squeezing. As you can see, it depends on r e power I phi p. So r is nothing but the squeezing strength, how much you want to squeeze your quadratures. And the second is in what angle or orientation do you want to squeeze the quadrature. And as we know, all we are doing this is to reduce noise or short noise in some particular quadrature. So this phi p is of really, really importance to us. And this is basically governed by the phase of the pump laser. That is this green light that enters. Whatever phase this has, the squeezing automatically governs by it. So in short, what we can learn from this is first we need to have an OPO, which is an optical oscillator, parametric oscillator. So what happens here is the pump laser comes and there is a crystal and then squeezed vacuum injects out of it. So also as we want squeezed vacuum, we do not want any bright light. This OPO is usually operates at the condition of gain is less than loss. So basically this 532 nanometer is the pump laser that comes in and 1064 nanometer squeezed vacuum goes out of it. Those are these dashed lines, as you can see, dashed red lines, because 1064 could be kind of seen as a red light. So what other thing is the pump laser that starts this process needs to be very much phase locked with the H1 laser that Sachin has already told about. This H1 laser is basically the local oscillator. The light should be in phase with it in order to see any changes or the interferometer to work. So this is very important. So how it is made sure is through this pump laser. So this pump laser is a 1064 nanometer laser, which is locked with the H1 laser. So this wire again goes to the H1 laser, which we had discussed earlier, and then it is now phase locked with it. But we do not want red laser. We do not want 1064. We want 532 nanometer, this green laser, in order to start our OPO. So we go through this second harmonic generator block, and this pump laser gets converted to the green laser. And then this basically drives the OPO. Now, whatever we discussed earlier, now the OPO is driven, now squeezed light comes out. But next, what we should wonder is how are we ensuring that the squeezing is done in the right quadrature? Because something different would affect the system in a very wrong manner. So, in order to make sure, we need to measure the phase of the vacuum light, right? That is it aligned in the way we want it to be. So, but how can you measure the phase of something which does not, which there is no light in it? It's a vacuum. So, solution was given in this paper of Walbruch that we need to have a control laser in the setup as well. So, what this control laser does is, first of all, it is phase locked with the pump laser. Pump laser initiates everything for this SPDC. It is also regulating this control laser to produce of in phase frequency shifted beam. So this is kind of looking like a yellow beam because it is shifted from the original 1064 nanometer or the squeezed vacuum wavelength. It is a little bit shifted. And the shift is about the order of a radio frequency, 29 megahertz. So the shifted beam, which looks like yellow, now it is produced by the control laser and it enters and mixes with this squeezed vacuum that is produced. So basically, you can think of it like we already had a vacuum laser, but we cannot measure it. So with it, we are coupling or sending a control laser beam, which is frequency shifted. Because if they are same frequency, we would later won't be able to separate them, right? So they together go together in order to as a reference that okay, the phase of vacuum squeezed vacuum is this by measuring this shifted beam. Now it mixes with the squeezed vacuum and enters the interferometer. Now in the interferometer, it interferes with the main light. So from the interferometer, from this antisymmetric port, the main light or the LO local oscillator light is coming along. which basically we are most interested in this signal. If there is a gravitational wave, there should be a change in this signal. So this is the major signal, this bold color red one. So it now enters and reaches a squeezing angle control photodiode where this yellow oscillator light and interferes with our control laser shifted beam light. And together, as they have a frequency difference of them, which is of the order of this radio frequency, they will produce beats, radio frequency beats, that because their frequency is not matching. So if they're completely aligned, there would not be that much beats, but if they are misaligned, we will see some beats. So as you can see from this from this beats, we can analyze how much phase difference is there between our control laser and our interferometer laser that is coming along from the port. And then you can see the green circles. This is basically the feedback. So what we do is we send a feedback to this pump laser that we initially discussed that starts off this SPDC. That okay, this much phase difference is there. You need to align it again or something like that. So that feedback is given to this pump laser and then it operates accordingly. Just to give you some numbers, what beat is measured along this control field, which is F naught plus 29 megahertz RF. It is now interfered with our local oscillator frequency, which is of the order of this terahertz. So more than terahertz, definitely. So when they are beat, so the difference between them is 29 megahertz. So the beat signal would be of 29 megahertz, which is RF. The electronics measure this. So if you think that if gravitational wave is there, the phase would also change. So, but that phase change would be of very lower frequency, audio range frequency. So that won't affect our feedback mechanism. So finally, what happens after all of this is we produced a squeeze light using the OPO in the SPDC conversion quantum mechanical description. And after that, we tried to measure the phase as much aligned to the quadrature that we really want to reduce the noise at. And finally, this thing reaches the detector. The other things like the yellow control light is now removed by the output mode cleaner because it just allows that frequency to reach. So now only the squeezed vacuum light, and the interferometer light, that the signal that we want to measure, reaches the photodiode. So the thing that we wanted to reduce, the short noise in the quadrature, is now reduced very well. So this was a wonderful fabricated engineering thought process in the paper that shows the squeezing in such nice manner. Finally, what we see in the output in one of the plots is, let's say the red curve is the typical noise when there is no squeezing, but when there is squeezing, we see the blue curves. And as you can see, this is the plot between sensitivity with frequency. So we want sensitivity to be as low as possible so that we get more precise results. So as we can zoom in also in our required range of frequency that we want to measure, like the 150 to 300 hertz range, there also we can see the blue curve is considerably lower. This is a log scale plotting, lower than the red one. So definitely we have introduced squeezing and we have reached sensitivity that is exceptional. Also, this was around 28% reduction in short noise. If we convert these things into numbers, that is 2.15 dB reduction due to squeezing. If we wanted to reduce this much noise in our system without squeezing, then we would have analogously had to increase 64% of the power stored in the arm cavity. So that is huge. Working with so much high power, every optics, everything would now deal with a lot of radiation pressure noise and various other noise would have been introduced. But lastly, the major question still remains. We introduced an entire squeezing setup. But did we bring any additional noise due to this setup? Because then the point would be defeated altogether if it is introducing additional noise. And the major thing we should look forward is the backscattering because there are so many optical setup introduced separately from whatever the interferometer that we have. It is apart from it. So if any scattered light backscatters by hitting some other objects and enters the interferometer, then it would bring along with it some phase, which we don't want. A parasitic phase, a false alarm that gravitational wave might be detected. In order to do that, the OPO that we have, the optical parametric oscillator. So basically that oscillator where the SPDC everything goes on, that is a bow tie cavity. It's a traveling wave cavity. It's not something standing wave like a Fabry Perot. So using this kind of configuration, there is no backscattering allowed because everything moves forward. So we reduced, or we did not have any 40 dB isolation, noise isolation was provided because of this technique or this engineering. And then we have Faraday isolators. So it is a huge topic in itself, but overall, if we go through, it's just that it allows the inject squeezed light, but it backscatters or rejects the backscattered light so that it does not enter our system. So overall, this entire method, Faraday oscillator or traveling wave, both external and internal design, has made the setup a highly sensitive setup up to date. And still, there are lots of developments going on. So what we understood from every these slides is we created a squeezed vacuum, we made it enter the interferometer, and we made sure the phase is aligned and there is no other additional noise. Next up, Bhargav, we will discuss whatever squeezing we generated. Were we able to measure that much squeezing at the end through the process? Was there any losses?
Yeah, so the experiment mentioned in the paper that they use squeeze state to reduce the noise in the system. So they injected 10.3 dB squeezing state in the system, but when they detected the noise reduction, they saw only 2.14 dB of squeezing is used. That is around 8.16 dB is lost in the system. So what are the reasons why the degradation of squeezing happened? So there are two main reasons. One is optical loss and another is phase noise. So these are the main reasons why degradation of squeezing happened. Now let's get in deep into optical loss. So as we learned in the class that optical loss can be represented in beam splitter coupled with signal mode and vacuum reservoir. If you see the beam splitter, port 1, 0, 2, 3, this is signal and vacuum. So if we want to measure the quadrature at this port and ignoring this one, we can write quadrature equation at port 2 like this. Meter P of 1. So this meter actually represents how much amount of squeezing is entering in the system. So now we can extract variance from the n delta x naught plus 1 minus delta p. Yeah, so now to extract the normalized variance, we need to divide this with vacuum variance. So the vacuum variance is 1 by 4. And now you can see this one, delta P of 1. So port 1 there is, we are sending vacuum. So the vacuum variance is always constant, 1 by 4. And we can convert this into another variable like this, V, and suppose V dash and B plus 1 minus meter. Here this term will get cancelled. Now as you can see, this V represents delta of x square by 1 by 4. So in our experiment, we are at port 0, we are sending squeezing state. So if we send squeezing state, the delta of x naught whole square, this will be minus e power minus 2r by 4. If it is anti-squeezed, then it can be e power plus 2r by 4. So then we can write this, we can say as V minus, this we can say as V plus. So we can convert this equation, V dash plus or minus neta minus plus 1 minus neta. So if it is plus, then we need to consider this variance here. If it is minus, you need to consider this variance here. So here you can observe if neta is 0, that means this entire term will become 0 and this exists. This corresponding to vacuum fluctuations. So if neta is 0, entire vacuum fluctuation enter into the system. That means more noise. If neta is 1, that means this term will become 0, entire squeeze state into the system. But this is the systems in the real world won't exist with neta equals to 1. So there are so much noises in the system. So in the paper, the experiment they have done, in their system neta is 0.44. That means 56% of there is 56% of noise exists in the system. So that are obviously due to optical noise and mode mismatch, all those things. Okay, so there was another reason also, the degradation of squeezing, phase noise. So it's basically the phase is between the local oscillator and squeezing state. We can represent the phase between this and phase between this. And if we measure the quadrature, so there is an equation, using that we measure the quadrature measurement, that is sine of minus this. So if you see here, there is LO. The quadrature measurement depends on phase of LO. So if phase of LO is 0, then we can get sine quadrature measurement. And if phi LO is pi by 2, then we get cos quadrature. Then we can rewrite this in terms of these phases, these two phases, like phi 0, like quadrature at 0 phase, then we get sine phi plus quadrature pi by 2 cos phi. If we extract the variance, equals to delta of x naught square sine square phi plus x pi by 2 cos square phi. Now again, if we extract normalized variance with respect to vacuum, this 1 by 4 delta of x naught square 1 by 4 sine square phi pi by 2 1 by 4 cos phi. Now there are two quadratures here, sine phi and cos phi. So if we assume that squeezing around cos phi quadrature, then the delta x pi by 2 variance will become e power minus 2r by 4. As we seen in the previous optical laws, we can represent this as v minus and x of 0 square. Now this will become anti-squeezed. As we are assuming cos phi is squeezed, then this sine term will become anti-squeezed. Then we can represent this. Then we can rewrite this equation, v plus sine square alpha phi plus v minus cos square phi. Here if you see, if phi is 0, then this term will become 0, this term exists. So here v minus is a squeezed term. So if phi is 0, matlab there is no any phase between these two, and this entire squeeze state will go into the system. If phi suppose pi by 2, then this term will get cancelled, this term exists. That means entire vacuum fluctuations go into the system. If it is not 0 or not pi by 2, that means we get squeezed and we get vacuum fluctuations. So the phase noise and optical loss both reduce the squeezing. So in the experiment, we got phase noise as 37 m radians, that is basically equivalent to 2 degrees. So there is very less loss due to phase noise, and but even though phase noise is very less, it makes significant change in the degradation or squeezing. So we always need to make sure phase noise is also very less to get accurate measurement. And as before, Shruti just showed the plot where you can see like this, and there is another one also very close. Suppose this is without squeezing and this is with squeezing. As I told, in the input squeezing was around 10.3 dB and the improvement only using 2.14 dB. Here mostly the without squeezing and with the squeezing, very that is not that much improvement happen. Very small improvement happen when squeezing is added because there is so much noise and squeezing is lost in the system.
Good evening. Now, I, Swam, will go ahead with the executable IPython notebook part of the presentation. So, just a bit again, introduction type. So, basically, the main idea is to check on the quantum noise in the interferometric measurements arise from the fluctuations from the two conjugate quadratures. So there is some theory written here so that we can look out. Uh, so the amplitude of the ideal noise h hat h tilde short is given like this, and it is proportional to the frequency and the storage time. Maybe. And that's one of the formula. And then the optical parametric oscillators, that's a power given, which we take as 10.3 decibel. It's from one of the papers. So the value is taken from there. And most of the values taken like the efficiency uh, and the residual phase noise, most of the values have been taken from the 2013 paper of Nature. What was it? Nature. Nature. I don't recall the full name, so pardon me. So the link is given here. So most of the values which we have taken is from this uh, paper of N Photon in 2013. So, and these are the derivations for the quadratures of the V plus and V minus, and we measured. And sensitivity improvement is taken as the inverse square root, 1 by square root of V measured. So that's just a bit look into the equations which we plotted. And I mean, today on that same path, this is the code which we'll take, and this is just to give the input of the generating, so the decibel of the generator squeezing, and this is V squeeze, and just changing the decibel into a variance range, and anti is 1 by v squeezed, and optical loss is taken uh, from the paper, the values, and this is phase noise. This with more calculations of this part, we prime so that it can be shifted a bit, and yeah. This is just at the end we measured and V sensitivity. So we take the frequency range in a log scale from 40 to 7,000 to get a long range out with 500 points in between. Sorry, 5,000 points in between. And yeah, it's short and every semantic, the noise and all is calculated in between. These are the formulae. Uh, And yeah, so this is the plot that comes out from uh, the frequency range from 40 to 7,000. And as you can see, the squeezing and then sensitivity in the lower frequency region is almost same. And it starts getting some increase in sensitivity while it, sorry, while it goes to the higher frequency. So there's a technical, like a good bottleneck which we can observe, which is between 100 to 500. There was another place where it was 100 to 300. Or yeah, we chose to look into the 100 to 500 range. So one of the main reasons is like this is one of the most uh, prominent region where most of the gravitational waves is found, like for BNS, I guess, BNS mergers and all. And yeah, so mm, this is something like a good, this is a region between the 100 to 500 frequency on how it unrolls. Here, there is an info technical noise. The green one is the squeezing noise. And yeah, so one can, that's it. Huh. So, yeah, matlab, it again shows that there is less difference in the lower frequency region, but yeah, uh, I mean, it also shows the how close it is to the other technical and matlab, on the other technical and semantic noises, and how it deviates from the estimated typical noise in the start, and how it passes one critical point like here. So yeah, I don't recall the exact thing, pardon me. So yeah, next was just to get a ratio. The maximum limit calculated is 2.16, which was calculated above here. Uh, Calculate measurable improvement. And this is just a squeezing enhancement ratio depending upon frequency, how much squeezing has been occurred with respect to the maximum point. So this is just a ratio given upon all the frequencies and plotted around. So yeah, these were the major plots, and then there was just some advancements like advanced frequency dependent a plot on advanced Legos, and it just showed like how they go. It is just a similar, it's a depiction plot. It's not, this is not much in here. It's just try to depict whatever the plot in the paper had. And but a rather more professional way to look at it, like in the above, we use NumPy and Matplotlib to generate our plots and use equations. While here we have some library, GWINC. Uh, so yeah, this library has a lot of noise budgets and in a more professional way. That is what we found, and this is one example of it. And budgeting of GW noise of budgeting of advanced LIGO, and as you can see, the purple line is maybe what we had been looking at initially. It's very similar in the value, and there are much more settings of it, like advanced plus and then cosmic explorer. So different instrumentation and different noise explanation here. So this is just a much more so it is like it's a version to for using in a better way, in a more concrete way. But yeah, the above was our implementation of the plots in the paper, and yeah, so that is what we have for the executable Python. I'll just run it once so that I should have run it while we were going. So pardon for me missing that. So yeah, as you can see, all of them have run again. So, yeah. No, so yeah, they have been run again. So as you can see, yeah, all of them ran again. So yeah, that's our executable Python notebook. And thank you.